Alright, so we're going to talk about stoichiometry. Stoichiometry is the topic we want to discuss tonight. So we're going to define stoichiometry to be the study of quantities of materials consumed and produced in a chemical reaction. So I like giving the example of the simple letters. When you observe the reaction between A and B, these ones we understand they are called the reactants. We understand those are called the products. So now the amount, the study of the amounts, the quantities of how much may be consumed here and how much is going to be produced there. That's where things like percentage yield comes in. We deal with the number of moles. All these are just like, we're just talking about the quantities of the reactants and the products in different measures and in different terms. All the things, the molarity, the concentration, they are all just quantities. And this is basically all we focus on under the study of stoichiometry. Okay? In addition to that, we also focus on the aspect of balancing the chemical equations. Later on, we'll talk about the ionic balancing ionic using ion electron method, as balancing acidic basic media. Of course, solution stoichiometry is another component we're going to deal with under stoichiometry. So it's a very interesting topic. Stick around so that we see whatever we've summarized in action. That's what stoichiometry is concerned about. Alright? So the first thing that I want you to understand is how we determine the number of moles. So I'm not going to say a lot about solutions tonight. I'm going to just talk about the basic first part, which is focusing on the masses, things to do with mass. So in terms of mass, we determine the number of moles to be given as mass over molar mass. I know most of you have mastered this formula for a long period of time. Now tonight I want you to understand the different way of answering questions other than that. Okay? So how are we going to be answering the questions? That's what I want us to basically get to look at. So let's say you're asked to determine the number of moles in, let's say, 32 grams of oxygen, for example. How do you determine the number of moles there? So instead of you remembering this formula, what I want you to understand is you can use the dimensions. If you look at the mass is what we have. Now, what other information do we know about oxygen other than the mass? Now, some of you know that if you check a periodic table, you are going to find what we call the molar mass. So the molar mass for oxygen is 15.99 something. Of course, if we round it off for the sake of our example, we're going to take it as 16. Now, because in this case oxygen is existing diatomically, there are 2. So 2 times 16 becomes what? 32, right? Becomes 32 grams. So now, what are the units of molar mass? It's grams per mole. So grams per mole, 32 grams per mole. So in this case, I'm interested in determining the number of moles. What do I do? Since it is 32 grams per mole, I want the moles to be on top. So it's going to be mole over 32 grams. And then I multiply by, I know I want to do away with, what? The grams. So I know if I'm going to cancel these grams, then the other gram is supposed to be on top. So we'll maintain the 32 grams coming from the mass. Maybe to make it, to just create a distinction, let me make that to be 34. 34 grams. So that as we put it there, it's going to be 34 grams. So you notice that the grams are doing what? Dividing. So even you without remembering that formula, you should be able to perform calculations under stoichiometry. And this is what I want to emphasize, that as we proceed, you need to build the ability to be able to answer questions in this form. So that at this point you see that it's going to be a division between 34 and 32, which gives us 1.0625 moles. So this is how you determine the number of moles as the simplest part of stoichiometry. I couldn't think of anywhere else where we could start from as we get to build a foundation. Are we on the same page so far?
Yes. So it's fine to listen.
Alright, alright. So this is very simple. I believe you already knew. Some of you know this formula before. And so can you mute your mic now as I continue talking? Alright, so
Hello. I just want to know the meaning of that N because I'm coming now. The meaning of number of mole, the symbols, their meaning.
the what symbols are you talking about?
I'm talking about the N equals to the M upon the MR. The formula. So the meaning of the symbol, so that we understand. Now, the number of moles. I understand the N is the number of moles, but
Okay, so N is the number of moles, M is the mass, and then MR is the molar mass.
okay, okay. Thank you very much, sir.
So is there a difference between molecular mass and molar mass?
Is there a difference between molecular mass and molar mass? There, there is a difference, I believe. Molecular mass, molar mass. But for the sake of explanations and for the sake of calculations, we can take them to be the same. So molecular mass, as the term entails, it's coming from the word molecule. Okay. So I told you of oxygen. Oxygen existed atomically, so I can call this an oxygen molecule. So the same 32 grams we had gotten after multiplying by 2, we can call it the molecular mass. Okay. Ideally, we can call the molar mass what you have on the periodic table, the relative atomic mass again. It's kind of, all these are just, they play the same law. What basically defines what they are is looking at what you have. Do you just have an atom? Do you have a compound? But at the end of it all, they can all be put there. Doesn't matter. Depending on what you're talking about. If you're talking about a compound, you'd have to just determine the modify, like add whatever you have there to get the total. So whatever you're going to get is what determines the name, but it doesn't really matter anyway. Yeah, others would call it the relative formula mass in terms of a compound. Yeah, others still call it relative molecular mass, but yeah, the difference really doesn't matter. They are all just like the same. I don't know if you guys are getting what I'm trying to say here. So if you're going to have
Yes, we're getting.
if you're going to have 10 grams of this, and then they ask you to determine the number of moles, how does it look like in calculations? How does it come out? So you're supposed to get the mass at 10 grams we have. Now, of course, since you want to find the number of moles, you have to find first of all the relative molecular mass. Yeah. So 10 grams multiplied by What's the molar mass of aluminium if you check your periodic table?
26 meter.
So 26.98. So let me now show you how you find the relative molecular mass. Have a relative formula mass. So it's going to be, for oxygen we've got 3. Let's say approximately 16. Aluminium we are saying what? 26.98. How many are they? There are also 2. So let's see what we're going to have. 3 times 16, 48. 26.98 times 2, 53.96 plus 48, 101.96 grams per mole. So that's going to be grams per mole. So it's going to be a mole over 101.96 grams. So that the grams can still divide. Of course, some of you still want to remember your formula. I have got no offense, no one will mark you wrong. Number of moles is equal to mass over molar mass. Okay, but I want to show you how the units come about, and this is very essential. It helps with complex questions that you're going to be dealing with later on. You know? So 10 divided by that, you come up with your number of moles. Okay. So I was just trying to show you to say what determines what you put as your molar mass is dependent on the formula of the compound you're dealing with. That's just the point I was trying to stress. Yeah. Everything else remains the same. So now, this is not basically the way the questions are going to be asked to you. The questions are going to be different. In that, what's going to be happening is you're going to be given an equation like that, and then they ask you, for example, to determine how much of C was produced after they've given you the amount of A, the amount of B. We'll get there, don't worry. I'm just trying to give you a picture. But it's very important for us to understand the small things like determining the number of moles, because that's going to be a very basic idea that helps us to build on other complex things we need to know. Yeah.
Yes, sir. Are they going to, in some questions, are they going to give us the number of the molar mass, the number of the atom? Sorry, the number of the atoms. Like for oxygen is 16. Are they going to include the number of atom in the question, or
So I don't know what you're asking. Well, just hold on a bit.
okay, 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 okay? Example like when when you've been asked a question and you are asked to find the number of moles, but in that question, are they going to include the number of atoms? For example, when they say oxygen equals to 16, hydrogen equals to 1, are they going to include the number of atom in the questions, or you are going to give the number of atoms while finding for the molar mass?
Okay, well, I believe I believe what you're asking is, are they going to give you the formula in the question? Are they going to tell you it's all 3 or is it all 2? Is this what you're saying?
No, not the formula actually. I mean, like if they are going to give you the number of atoms, like if they say oxygen equals to 16, the number of atom for oxygen equals to 16, like finding for the molar. Example, when you've been asked to find for H2O, then H2O, the number for atoms for hydrogen equals to 1 and oxygen equals to 16, then you're going to include it in the
Okay,
question.
okay, okay, okay. So we don't call that the number of atoms. we don't call it the number of atoms. So in every chemistry test assessment, you're going to have what we call the periodic table. So all that information is going to be there. You don't have to worry about that.
Thank you very much.
Okay, let me take you to the next part now. I want us to understand how we determine the number of atoms, number of molecules. These are the basic things I want you to know tonight. Number of ions. I also want you to understand how the values that you see on the periodic table. For example, for carbon, you know that it shows 12.01. How did that value come about? I know you guys know about isotopes already. So we understand how you use the isotopes also to help us get the relative atomic mass value. Okay? These are the essential concepts I want you to understand tonight. So that next time we'll get into a complex part of this topic. Okay? So we'll start by looking at how we determine the number of atoms. How do we find the number of atoms? How do you go about it? So you've all come across what we call the Avogadro's constant, right? 6.022 times 10 to the power what? 23.
23.
So I usually say the units are per mole. So if you are asked to determine the number of atoms, it's going to be the Avogadro's constant is going to change to atoms per mole. So ideally, if you want to determine the number of atoms, it implies you have to cancel out the mole there. So it means you just have to multiply by the number of what? Moles. So if you are going to ask you to determine the number of atoms in oxygen, okay? If let's say oxygen O2, right? And then they tell you to say maybe like we had said initially 34 grams of oxygen. Determine the number of oxygen atoms contained in 34 grams of oxygen, which is existing atomically like that. Well, I would actually start by saying the number of oxygen molecules. How do you determine the number of oxygen molecules? So when you look at O2, this is an oxygen molecule. So how many are they in 34 grams of oxygen? How do you answer that question? So multiply by the number of moles. So look at this, look at what you've been given. All you just have to do is determine the number of moles. Determine the number of moles. So you know that to determine the number of moles, we've already talked about that previously. You've got the mass there, you've got the molar mass. So we find the molar mass of the molecule. You'll notice it's going to be 16 times 2, 32. The mass divided by that 32. The number of moles we had calculated, if you wrote down somewhere, is what?
We can't see what you're writing.
You all can't see what I'm writing.
Yes.
Can you see anything on the board?
No, we can't see anything.
You can't see anything. Okay, wait. Is it just now or you've not been seeing anything from the start? Class, can we see what's on the board?
Yes, we can see now.
Yes, 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 you can see.
You can see now. You are not seeing before.
I can't see personally. I'm not seeing anything.
Okay, just leave the meeting and rejoin. You should be able to see what's there. Okay, so if you look at the information there, O2 and 34 grams, you're able to find the molar mass from the oxygen there. So these are the number of moles I'm getting. I already showed you how we calculated that. So you notice that the number of moles will now be cancelling out. What's going to end is you multiplying the Avogadro's constant with that number of moles. You notice that the units you're going to have will be molecules. So what that implies is you would have calculated the number of molecules. Are we together? You would have calculated what?
The number of molecules.
The number of molecules. The number of what molecules? Oxygen molecules. Right? Now, how does the question, how can we handle it differently if the question was the number of atoms? How can we handle it any different? So now, number of atoms, you know what an atom is, right? Do you know what an atom is? What's an atom?
The smallest unit of matter.
So when you say O2, 34 grams, how many oxygen atoms are there?
2.
So there are 2 oxygen atoms in what? In one molecule of what?
Oxygen.
Okay, so we have 2 atoms in one oxygen molecule. 2 atoms of oxygen in oxygen molecule. So if we're going to determine the number of atoms, it will be different. We won't just multiply by the number of moles. So if we are going to say we're determining the number of atoms, the number of moles we're going to get of that is we're getting the number of moles of the oxygen molecule. So the value we add 1. I want you to pay attention to what I'm saying here. It's going to be 1.0625 moles per what? This number of moles we have to pay attention per oxygen molecule. Now, are we interested in the oxygen molecule? No, we are not. We're interested in the atoms. Now, we know that in each oxygen molecule, we have how many atoms? How many atoms do you have?
2.
You have 2. So, you are supposed to add times 2. In short, what I'm trying to say is the number of moles we have is representing the molecule. Now in each molecule we have two atoms. So because ideally you know that if I'm going to put if I'm going to put molecules there, where does the formula end? The formula ends only by multiplying by the number of moles. So in other terms, if I'm asked to find the number of atoms, I can decide to just calculate the number of molecules. Now, after I calculate the number of molecules, I know that in each molecule there are 2 oxygen atoms. So I can just multiply by 2. I would have gotten the number of what? The number of atoms. I don't know if you're getting the logic that I'm trying to use here to help you get the idea. Are you getting it?
Not really.
Not
They
yet,
say
not
that
yet.
not really.
Do you understand the difference? Do you understand the difference between a molecule and an atom?
Yes.
What's the difference? What's the difference?
The atom is the smallest particle, then the molecule is
No,
the
no, no, no,
largest.
I don't want that definition. I want you to when I say what's the difference between O and O2?
Or
Okay,
it's
the
monoatomic, and then O2
atomic.
it's diatomic.
Which one is an atom here?
Oh,
This is an atom.
both both the atoms.
This is an atom. This is an atom. This is singular. That's the atomic. But this is a molecule. A molecule is a combination of what?
Two
Of
atoms.
two atoms.
Of what?
Two
Two
atoms.
atoms.
No, I never said the molecule is a combination of two. It's a
Yes.
combination, not two elements. It's a single element
Two
there.
or more atoms.
Two or more. So there are going to be cases where we are going to have all three as well. But I'm trying to just help you understand that. I'm trying to help you distinguish on how you determine the number of molecules. So when the question asks you to find the number of atoms, and I want you to pay particular attention. If a question asks you to find the number of anything, it may be number of atoms, number of molecules, all right? The formula is always going to be per mole. That's the formula. So if we were given 10 grams of this oxygen atom, they ask us to find the number of atoms. What are we going to do? We'll just say, okay, since we know that we only have that single atom, right? We only have one. So all we just have to do is just find the number of moles. You would have gotten the number of atoms already, right? Now, how is it different when it's O2? It's different in a way that the number of moles you are getting are number of they are moles of what? The number of molecules. Or in other terms, let me change let me use my terms carefully. If I'm going to use the number of moles of O2, it means I'm determining the number of what? The number of O2 molecules. How many O2 molecules do we have? How many oxygen or how many diatomic molecules of oxygen do we have? That's what it means. I don't know if you're getting the picture. So whatever we're going to get at the end of it all is going to be the number of oxygen, what? The number of O2. So if you want to get the number of atoms in this case, singularly, you'd have to multiply by 2. So that it just becomes oxygen atoms because of this subscript 2. Now, if your question is just molecules, molecules can be any number, so you just leave it the way it is by just multiplying by the number of moles. That's the difference. So when they ask you to find the number of atoms, when you've got a subscript, after you multiply by the number of moles, multiply by the subscript. That's the point I was trying to make. I don't know if it doesn't make sense, it's fine, we can move on. I hope you've gotten an idea.
Let's move on. Let's move on. Let's keep on.
So you should understand the difference between a molecule and an atom.
Yes, sir. Yes, sir. Yes, sir.
Now the other concept that I want us to understand is maybe even before that, let's look at a few questions just on the same, because this concept is very, very important and you'll see it later on, especially under electrochemistry later on. It's going to get back under electrolysis. So let's determine the number of atoms that are contained in 10 grams of aluminium. So let's determine the number of what? Number of atoms. What should we do? So I said whenever they ask you to determine the number of atoms, number of molecules, just what should come to your mind first is Avogadro's constant, and then the units are going to be defined by what they want you to determine. In this case, they want you to determine the number of atoms, so it will be atoms per mole. Now, you and I know that aluminum doesn't exist atomically, so aluminum is just Al, okay? So it means it's just an atom. So there's nothing like multiplying by what? It's just aluminium. So all we just have to do is to find the number of moles of aluminium. Now if you check your periodic table, what's the molar mass of aluminium? It's 26.98 grams per mole. I already showed you guys how to determine the number of moles. So you've got a 10 grams, divide by the 26.98. What I'm getting is something like 0.37064 moles. So we have moles. The moles can divide. What remains? We remain with a number of atoms. And that's how simple it is. So just multiply this Avogadro's constant with that number. I've shown you what has happened to the units. What remains, what's standing out is the number of atoms. And that is all that is expected from you. Have we gotten that?
So yes, so that Avogadro's constants divide by more. It's just part of the formula so that we cancel the moles, the units for moles.
It's always going to be
Is
per
that
mole. It's always going to be per mole. It may be molecules per mole, it may be ions per mole. It's always going to be per mole. So I'm trying to show you this to understand that each time, know that you have to multiply by the number of moles so that you can cancel out. Not that it's there that it should be cancelled out. No, it's part of the units.
alright?
Anything else? Have we understood this concept? This concept is very important.
Is there a situation whereby you're given a number of moles and you're only asked to determine the number of atoms?
Well, obviously that's going to be too easy for you, so it's possible it may be there, but I want to give you the complex part of it. So if a number of moles are given, no need of you to calculate the number of moles, then they're given. Just plug in. Okay? Now let me show you how you find the...
Yes, and is it like mandates that you're supposed to?
that you're supposed to do what?
Like is it a mandate for you to like for the number of moles when you're answering a question containing the number of atoms, is it always that you are supposed to find the number of moles using the that that formula for n is equal to m over m, or you can also find the number of moles in a different way whereby you're given the mass and then there's another maybe formula where you can find the number of moles without using the atomic mass.
Okay, but you people are thinking too much. Don't worry. Like I've said, there are a lot of formulas of determining the number of moles. Yeah, we'll get there. We'll get there. Yeah. For now, I want you to and I'm very much. I've been actually. This is like my fourth year teaching so I know what you need to know. So don't worry. I know the things I'm explaining look simple, but just try to understand them for now, and I would expect you to have known them later when we reach there. Yeah. So I know what you need to know. Don't worry. I'll make sure I talk about everything that you need to know. Yeah. I don't want to cruise you, but just stick around. Okay. So I told you I also want you to understand how you determine the relative atomic mass. Of course, I told you to say you have to understand how to determine the number of atoms, molecules, ions. You know what ions are? Things like sodium chloride. So as well for sodium chloride ion, if they gave you the mass, you can find the number of moles by using its molar mass. So in such a case, when you're determining the number of, yeah, what you're going to be determining will be called the number of ions, but it will still be the Avogadro's constant, and then ions, and then it will be ions per mole. So that's the way it is. You know what ions are. So it's the same concept: atoms, molecules, ions. Usually it's a bit complicated for the atoms when you've been given a molecule. It's not even complicated, you just look at the subscript. When they give you a molecule and then they expect you to find the atoms, that's when it's different. Now, for the relative atomic mass, the values that you see on the periodic table, the values you see on the periodic table are not really the actual. If you're going to get copper, if you're going to get a copper atom, assuming it's possible for you to get one, it's not necessarily that you're just going to find the molar mass of the one that's shown on the periodic table. No. If you look at carbon, if you get carbon, you get graphite, I don't know, get a single atom of it, it's not necessarily that it's going to be 12.01, okay, grams per mole. No, this value is a relative. That's why it's called relative atomic mass. So we determine relative atomic mass by using the isotopes of every element. So what are isotopes? This is a very simple question that you should expect even at this level, that they can still ask you to define what isotopes are. Isotopes, give you examples of isotopes. I don't like defining them. Carbon 14, carbon 13, carbon 12. These are the isotopes of carbon. Now carbon, we know that it's got a proton number, atomic number of 6. So isotopes, we can see that these are the same element. It's the same element, different what? Mass numbers. These are atoms. So atoms of the same what? Of the same element. With what?
Same atomic number with different mass number.
So same atoms of the same element with different mass numbers. If you want, you can add the part of the same atomic number, but it's obvious it's the same, so different mass numbers. The atomic number is what determines the kind of element you're dealing with, so expect it to be different for different elements. So atoms of the same element with different mass numbers. Those are that's what isotopes are. So we use these isotopes to help us determine the relative atomic mass of an element if you look at the periodic table. So they expect you to know that because they are going to give you the isotopes like the way I've put them for you. They are going to give you this and then expect you to determine the relative atomic mass. There are going to be cases where they will ask you to determine their percentage composition. So in this case, for this example tonight, I'm going to give you the percentages. So copper 12, not copper, carbon 12 is 98.89%, carbon 13 is 1.11%, then carbon 14 is very small, less than 0.01% abundance. What that means is, if you are going to get, maybe idea this, if you get a component of carbon, you find that 98.89% of that is going to be carbon 12. 1.11% of it is going to be carbon 13. Okay? So what then should we put on the periodic table? We can't put all the isotopes there. We need to put one value that will represent them all. So you determine the relative atomic mass by multiplying. You multiply the same mass number that is different, okay, by its percentage. So for each one, you continue doing like that. There are going to be some isotopes where we're just two isotopes for an element. There are going to be cases where you can even have four. So the formula continues adding up. Okay. In this case where we only have three, so let me use these very values and see what we can get for our calculations. I won't use the actual values. Because the 14, 13 and the 12 you are seeing are just rounded off values. For example, carbon 13 in the actual case it's like 13.00034, but I don't want to waste time with those points, but in the actual sense you're supposed to use them in practice. Okay, so let's try to use the exact numbers we have: 13, 12 and what. So for the first one, carbon 12, I'll start with a 12. So we have 12 as the mass number multiplied by the percentage 98.89%. Percent means over 100, plus carbon 13 percentage 1.11%. And then now if you look at 0.01 divided by 100, that says, for me that is useless. I can even omit it if I want. 14 0.01 divided by 100, that's too small to make a difference. So grab your calculator and try to compute this and see what you're going to have. So 98.89 divided by 100 is 0.9889 times 12 plus 13 multiplied by 0.0111. So 1 2. So I've disregarded the last part, is useless to me, it's too small. So the value I'm getting is 12.01111. So if you check the periodic table, you have 12.01. So you've seen where it's coming from. So this is something very simple and straightforward. This formula is very simple. Just the mass number multiplied by the percentage plus the other one plus the other one. You'll be able to get the relative atomic mass straight away without any complications. Okay? Are we on the same page? So we usually add a U to present atomic mass.
Yes, we've understood. I have understood.
Okay. So for your practice as we end the class, copper 63 and copper 60.
Wait, I have a question.
Yes.
So, what is the actual, like, relative atomic mass? Why is it important?
Why is it important? I've never thought of that.
Mm,
But ideally, I think it's important in that you don't want to have a complicated periodic table. You don't have to know you don't have to use all the values of the different isotopes. If you're trying to talk about, it's like you have a representation of the whole thing. Come up with the average and come up with something simple. Imagine having a periodic table which is having I don't know how many elements because of so many isotopes. Wouldn't that be too hard for you to locate the element you're looking for because of so many isotopes being shown on this?
it would.
Yeah.
It would.
So come up
Alright,
with.
thank you.
All right. Okay. Good question. You can even go and research more about it and tell us next time we meet.
Okay. Alright.
So copper 63. There is a certain concepts that you know, and then they'll never ask you about the application and all, unless if you are interested yourself. And it's very actually it's good for your learning. If you appreciate the importance of something, It'll be easy for you to remember it. So copper 63, copper 65. This is 69.09%. That's 30.91%. Now the actual value of copper 63 is 62.93. The actual value of copper 65 is 64.93. So I want you to share your solutions to the group. Determine the relative atomic mass of copper. Okay, are there any questions?
You're going to show us how to determine the percent composition on another day, or it will
I'll show you at another day. Yeah. Did you learn about it already? Okay. Yeah, this is where we end for tonight. I don't want to give you a lot of data. This is chemistry. I want to be very sensitive on how I give you the data. Next time, we'll use a different approach. This was an introductory class, so next time we'll use a different approach. We'll be answering questions like we've been doing in the other courses. So answer questions next time. We'll get a tutorial sheet and then start answering the questions. Okay, so I hope you've learned something even as you get to sleep tonight.
thank you, sir. We appreciate.
All right. So